Hello and welcome to Chapter 3 in Foundations of Math. We'll be taking a quick look at the PowerPoint notes. So if you want to print those or access those from your multimedia library, you can do so. You can also use your formula packet found under document sharing if you want to just jot some notes down next to some key facts that are already summarized for you. The first section in Chapter 3 takes a look at some of the beginning material for symbolic logic. Of course, the first thing we need to look at is what is a mathematical statement. Simply a sentence that's either true or false. It cannot be both because we have what we call the law of excluded middle. It's either true or false, but not both simultaneously. So things like commands and questions, opinions, they're not statements because they can't be true. They can't be shown to be true or false. We will be using letters like P, Q, R, and S to represent statements, kind of arbitrarily here for some examples. And we can even do something such as negate those. So if you have a false statement, you negate it, it's now true. And if you had a true statement and negate it, it's now false. Some examples for you to read through and think about. Now the notation here, you'll notice in front of the P and Q, you see that little tilde symbol, and that indicates not. So if I write that symbol, the little squiggle, if you will, to the left of the one on your keyboard, that symbol indicates to negate the statement following. We can talk about what quantifiers are. Quantifiers are words that answer the question, how many? There are universal quantifiers, which would be the words like all, some, or none. And then there are existential quantifiers, there are universal quantifiers, which are all, every, each, or none, and existential quantifiers, which would be like some, at least one, at most, meaning not all of them. Make sure you take some time to read through this and think about the equivalent ways of wording quantified statements. So for example, if we say all of something, then you're referring to the fact that every single person or every single thing in that group applies to that. So there are none that do not have that characteristic. If you say some, all you're saying is that there exists at least one that meets that requirement. Now that's kind of important because if you then negate a quantified statement, you want to be able to keep this straight. So if you say, for example, all students hate mathematics, the negation would be that some students do not hate mathematics. You don't have to say an all or none. You simply go from some to all or some to none. If I say some students like mathematics, meaning there's existing at least one student who likes it, the negation would be that nobody likes it. An example for you to read through, negating a quantified statement. In the end here, we conclude that some of the piston rings were not replaced. Okay. We're going to jump to our second section, and again, just doing a quick walkthrough of the material, looking at compound statements and connectives. Just like in English, you can have simple and compound statements. A simple statement would be like a simple sentence, where you're simply expressing one idea. If you have a compound statement or compound sentence, you're connecting two thoughts together. So in mathematics, we can connect two or more simple statements using a connective, and, or, if then, or an if and only if. If we want to express an and statement, we use the upside down V, and that symbolizes for us the word and, otherwise known as conjunction. If I write, it is after 5 p.m. and they are working, I will have P upside down arrow, or upside down V, Q. If I want to say it's after 5 p.m. and they are not working, I will have P upside down V, not Q. Take a few minutes again to read over and reflect. There are different ways to express this. You could say P and Q, P but Q, P yet Q, P nevertheless Q. And they can sound a little bit different and still express the same concept. You can also use an or connective. An or connective is a little more relaxed. It can mean two different things. It means that you could have been one or the other or both. It could be exclusive or it could be inclusive. So this is called a disjunction, meaning it's P or Q or both. And again, if we read through, the bill becomes majority approval or the bill becomes law, P or Q, upward arrow V. An if-then statement is denoted when you see this arrow. This is what's called a conditional statement. The part that comes before the arrow is called the antecedent. That's the part that has to happen, and then the consequent follows. So if P, then Q. And you can read over another statement here where they kind of write through negate Now this chart is pretty important for the following reason. Not every statement that we make is written if P then Q. For example, we might say, here's the consequence, as long as this first part was satisfied. For example, let's start off with a silly sentence. If I am stressed, then I eat chocolate. I could also say I eat chocolate if I'm stressed. It's still saying the same thing, even though the wording is different. I can also say being stressed is sufficient for eating chocolate, or eating chocolate is necessary for being stressed, and so on. A biconditional statement, or if and only if, means that the statement is still true even if we reverse the antecedent and consequent. So this is abbreviated IFF, and it's a double arrow for the conditional statement. Again, take some time to read through and think about these interpretations, such as the bottom two is necessary and sufficient for. So quick summary. This particular slide has a nice quick summary for you of the notation, the little tilde symbol for negation, and, or, if then, and a biconditional if and only if. Make sure you're then able to express symbolic statements with and without the parentheses, or being able to read and translate. So for example, P and Q, she is wealthy and she is happy. The negation says it's not true that she's wealthy and happy. Or B, she is not wealthy and she is happy. Or she is neither wealthy nor happy. Or you could say here in letter C as well, you could say it is not the case that she is wealthy or happy. Again, just like mathematics, where we have numbers, you have an order of operations. So things done in parentheses are going to be taken care of first. And so again, be careful as you're reading and decoding the symbolic statements. Now we do need to think about what's called dominance of connected. If you do see a string of symbolic notation and there are no parentheses there, how are you supposed to know which part you do first? The statements before and after the most dominant connective should be grouped together with parentheses. The least dominant is negation, then it's the conjunctions and disjunctions, conditional and the biconditional. So for example, if you saw the first statement here, P arrow Q and not R, the P arrow Q part, well, that would be dominant because the if then is a stronger dominance than the and or the or. So you're going to put the Q and not R in parentheses and do that first, and then you would be thinking about your if then. Okay, and again, some examples for you to read through and think about. Here again, the dominant connective is the if and only if. So in your mind, you can think I have to do Q and R first, and then do my if and only if. Okay, we're going to take a look at our next section now, where we start to take a look at the different cases that can occur with these. And in order to kind of organize that information, we're going to use what are called truth tables. Negation simply means that we write the opposite. So if P was true, then the negation is false, and vice versa. When we talk about a conjunction, however, you want to be able to think about more cases, since then you're talking about two symbols. If you're using two different statements, P and Q, you have to recognize that there are four possible cases. They're both true, they're both false, one is true, or the other is true. So we want to think about, what does the conjunction mean? P and Q. The only time you will get a consistent truth value from this as a result of your statement would be if P and Q are both true. As long as one of them is false, your final result value is false. A disjunction is less restrictive. As long as one of them is true, the final truth value is true. So if you're comparing two columns where you're looking at P or Q and they're both true, you get true. If you're comparing P or Q and one of them is true, you still get a true. The only time this is false is when they're both false. You can read through these. Now in the next step here, we're going to take a look at constructing a truth table for the negation of P and Q. So you start off by doing P, true, true, false, false, and Q, true, false, true, false. That nicely gives you the four pairs, if you will, of trues and falses. Then you have a P and Q. Remember, this is true only when they both are true, so we're comparing true and true. It's true. True and false is false. False and true is false. False and false is false. Now the next column is the negation. That's the final thing we're going to do. We're going to take the column we just created and negate the content. So the opposite of true is false. The opposite of false is true. Opposite of false is true. Opposite of false is true. Here's a more involved table. Again, we would start off with P and Q. True, true, false, false, true, false, true, false. Always the easy part. And then we're going to need to have a negation of P inside our parentheses. So we start off by doing a not P column. False, false, true, true. Remember, it's the opposite of whatever P is. The next thing we're going to do is compare the Q and the not P column using an OR. So as long as something's true, the answer is true. So we have true or false, that's true. False or false, that's false. True or true, it's true. False or true is true. The next thing I need to do is have a not Q column. So that's the opposite, of course, of Q. False, true, false, true. And then I'm going to compare these two columns using an AND statement. The only time I will get a true result from an AND statement is if they are both true. So I've got a true and a false, a true and a false, a true and a false. Those are all going to be falses. Only my final line is true. Now, of course, if you added a third statement, if you added R, you will now have 8 different cases. And again, it's consistent and best practice to simply always fill them in the same way. If you do have 8 cases, go true, 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 false, 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 true, true, false, false, true, true, false, false for Q, and then following the pattern for R. That way you're bound to get all 8 cases. They're all telling you they're all true, they're all false, some of each. And then again, here's an example where we're constructing the truth table with 8 cases and working through the patterns. Notice here that this one is true, the example where they're looking at it. Take some time to kind of read and think through this. And again, do it one column at a time. P and Q, so you don't even worry about R initially. P and Q. The only time an AND is true is when they're both true. So it's true, true, and everything down the column, the rest of the time it's going to be false. We then compare that column with R. But we use an OR. So as long as we have one true, the answer is true. True, 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 false, true, false, true, false. So again, the OR is less restrictive. As long as you have one true for both trues, your answer is true. If you need to determine a truth value for just a specific case, then you will be extremely happy. You won't have to do a particular truth table. You can just simply do a straightforward row. So for example, we have a P, Q, and R based on that prior graph. P is true, Q is true, R is false. So we want to look at a specific case. So we substitute P is true, Q is true, R is false. Now inside parentheses here, we have true and true, which is true. And then we negate the true, which means we're going to get false. And we negate the false, which means we're going to get true, false, or true. The final result is going to be true because a disjunction is true when at least one of your parts is true. So we could say for that specific case, for when P and Q are true and R is false, the final value of our statement is that it's true. Moving on to section 4. Continuing on with the idea of truth tables, we're now going to take a look at the if-then. Now, the key thing to remember with the if-then is that there's only one time it's false, and that is when the if part happens, the antecedent happens, and the consequence did not. In other words, in a sense that the if part, the antecedent was true, and the consequence should have followed, logically, also be true, and it wasn't. So true to false is false. Any other time, they're true. I like to use the example as I do in class. For example, if I got elected, I'll have taxes go down. So if I get elected and taxes go down, then you're happy. The statement was true, I told the truth, things went the way they were supposed to. If, however, I got elected, truth, or P, and taxes did not go down, then you call me a liar. If I don't get elected but taxes still went down, in our third case, you're happy because the end result is something that you wanted. And of course, I'm innocent until proven guilty in the bottom row because I did not get elected, taxes did not go down, but you can't say that I lied. So it's basically still true because you haven't had the chance to prove otherwise. The only time a conditional statement is false is when the antecedent is true and the consequent is false. Keep that in mind and make it a lot easier when you're dealing with this symbol in the chart. So an example truth table, we're going to go from not Q to not P. So we negate the Q column, false, true, false, true. We negate our P column, false, false, true, true. And now in your mind's eye, you're going to connect each of these with an if-then. False to false, well, that's true. True to false, oh, that's the case. You don't want to forget that. That's the one where your value is false. False to true is true, true to true is true. So 3 of them are true. The only one that's not is the particular case where we went true to false. Now, if you reverse and negate the antecedent and consequent, the statement's truth value will not change. So, in other words, if you negate both P and Q and turn the order around, you still get the same value, and that's what they're proving here in this table. And it's worth your time to sit here and, kind of think through and work through this. First we do P or Q in the parentheses, then we find not P, and we combine those 2 columns with an and. Remember, with the conjunction, the only time your answer is true is when they're both true, so we only have 1 row where they are both true. However, we're then going to take this column that we just computed from inside the brackets and do an if-then to Q. Now, I would highly recommend that you would copy your Q column again here, right where I'm kind of running the mouse. Put another little Q column, true, false, because then it's easier for you to see false to true is true, false to false is true to true is true, false to false is true. This is an example of what is called a tautology, when the truth value at the end of your truth table are all trues. A biconditional, or the double arrow as many students like to call it, the if and only if, this is only true when the component statements have the same value. So if both P and Q are true, or P and Q are false, then your final value is true. Slide 9 here is a great little summary of your symbolic logic. You can kind of review over here in words what each symbol does. And then read through the example, because you could be a super $1 million prize entry winner. Or not. You can't sue them if you don't make the money. Okay, moving on, we're going to continue on with section 3.5 and take a look at the objectives having to do with conditional statements and equivalent statements. If we want to talk about equivalent compound statements, they're made up of the same simple statements and they have the same truth value for true-false combinations. So for example, you can prove this using a truth table, because if you get the same results down 2 columns in the truth table, 2 things you're comparing, like true, true, false, true, that was one statement, P or not Q, and another one was not P to not Q, and we got true, true, false, true. So we could say if P or not Q, and get the same truth value if we said not P, if not P, then not Q. So what that actually is here, if we say P, if P, then Q, and then that's the same as, or logically equivalent to, not Q, arrow not P, if not Q, then not P. That is an example of what is called a contrapositive. So the conditional statement and its contrapositive are going to be equivalent. So for example, if you live in Los Angeles, you live in California. So if you do not live in California, then you do not live in Los Angeles, because it's contrapositive, and logically they say the same thing. You can also take a look at what are called the inverse and the converse of your conditional statement. The converse, you turn them around. If Q, then P. And the inverse, you negate them both, but you don't change the order. The inverse and the converse are equivalent, and the conditional and contrapositive are equivalent. So here's a statement. If you are 17, you are not eligible to vote. So you want to find the inverse, converse, and contrapositive. So if you are 17, you are not eligible to vote. The converse, turn them around. If you're not eligible to vote, then you are 17. The inverse is negate them both. If you're not 17, then you are eligible to vote. And the contrapositive, turn them both around and negate them. If you are eligible to vote, then you are not 17. Notice the first and the fourth one are true, and the 2 in the center, the converse and inverse, are not necessarily true. So the converse and inverse are logically equivalent, and the conditional and its contrapositive are logically equivalent. A nice short little section there, although it still is probably going to stretch your brain just as much as any other section. Now, moving into 3.6, we see something that we've seen before in a name in set theory, and that is De Morgan's law. So we're first going to take a look at the negation of a conditional statement. How do you negate an if-then? Well, a lot of people think, well, I just negate P and negate Q, but that's not the case because that's an inverse. That's not a negation. What if somebody made a promise to you, like, if you work hard in this course, you will get an A, and you worked really hard and you did not get an A? You would feel as if you were lied to or gypped, or that the part that was supposed to happen, that result you were looking for, that high grade, did not occur. The negation of a conditional statement is written as the if part does happen and the consequent, the then part, does not follow. So the negation of if P then Q is P and not Q. For example, if too much homework is given, the class should not be taken. So the negation, what would that look like? Well, the negation would say, too much homework is given and the class should be taken. Again, quick summary of the conditional statements: inverse, converse, contrapositive, negations. And that leads us then to thinking about De Morgan's law. If you recall from set theory, when we studied the set theory, if you kind of had the complement of the union, it was the same as the intersection of the complements. Kind of almost looked like a distributive property, sort of. And we sort of see that same thing here. If we negate a conjunction, it's the same as the disjunction of the negations of the individual statements. So the negation of P and Q is the same as the disjunction, or not P or not Q, and vice versa with the disjunction and negation. If you use a truth table to prove this, you will see that both columns match: false, true, true, true. And here is written out a little bit further, kind of fleshing it out for you if you're going to be writing statements with that. For example, it says, write the negation for the following: all students do laundry on the weekend and I do not. Some college professors are entertaining lecturers, or I'm bored. Negation, of course, we know college professors are entertaining lecturers. Remember that from section 1. You're going from an existential to a universal quantifier. You switch the or to an and you negate the I'm bored to I'm not bored. Again, allow yourself some processing time as you think through these statements, because it's very easy to kind of get distracted and lost along the way. Now you can tell, as the truth tables become a little more complex, that there's probably a reason that we're doing these, aside from just tormenting you and challenging your brain. One of the reasons we use truth tables is to analyze arguments and to determine if particular statements are valid or not. An argument consists of primarily two main components. First, it has premises, which would be your given statements, or, quote, statements of fact, if you will. And then the conclusion would be the result determined by the truth of those premises. You have a valid argument if the conclusion is true when you presume your premises to be true. You have an invalid argument, of course, if that's not the case, and sometimes we also call that a fallacy, and you can use a truth table to test that. Now, using a truth table to test the validity of an argument can be a little time-consuming and a little bit aggravating if you're not paying attention to detail, or if you waited to the last minute to try to finish your homework. What you're going to do is write out your premises, and then you take your premise and you use the conjunction and, so premise 1 and premise 2 and premise 3, however many premises you have. Most of it will work out just like 2 or 3 premises. So we're going to take premise 1 and premise 2, combine them, and then do an if-then, a conditional statement with a conclusion. If your final column has all truths, or what we call a tautology, then the argument is valid. If you do not have all truths in the end, it's not a tautology. So there's a particular example here where we convert from the words about Mr. Scott and Star Trek into symbols. So we have if P then Q, and then Q, is it safe and logical and valid for us to assume P? So what we would do is we would start off by saying if P then Q, and conjunction with Q, complete the truth table. Our final statement then will be the result of that column with a conditional statement with P. If our final results are all truths, then it's valid. So let's take a look. We're going to start off with P and Q. Again, true, true, false, false, true, false, true, false. If P then Q, remember the only time that this particular statement would be false is if we start with true and we go to false. So true to true is true, true to false is false, false to true is true, false to false is true. The next thing we're going to do is take the results of that column and a conjunction with Q. So true and true is true. False and false is false. True and true is true again. False and true is false. Remember, when we're dealing with a conjunction, it's only true when both symbols are true. Now again, after this fourth column here, I would actually squeeze in a little column where I would rewrite P. True, true, false, false. Because I'm doing an if then, and it kind of helps me see it from left to right instead of having to kind of look back to the beginning of my chart. Students tend to sort of get a little disoriented with that, so it's really helpful. Make another little column in here and just pop in your P. So true to true is true, false to true is true, true to false is false. Remember, that's the only time a conditional is false. False to false is true. So what does that mean? You get to the end, you're like, oh, I don't know, I'm just done with my truth table. Well, this does tell us something because we do not have all truths at the end. That indicates that Spock's argument is invalid, or what we would call a fallacy. So we've given another example from Henry Brommel. And so we convert to symbols, and we do our truth table, and this time it all comes out to be truths. Take some time to work through that and kind of walk yourself through that process. You should get all truths. So that means his argument, his statement, was a valid argument. Imagine doing this for some political speeches. Now, if you're like most students, you're probably thinking, oh, I have to do that for every single argument kind of question. The answer is no. If you're fortunate enough to be able to put your argument into symbolic notation and match one of these forms, then you do not need to do a truth table. You can simply say, yes, it's valid because it looks like a contrapositive reasoning. Or no, it's not valid, it's invalid because it's misuse of disjunctive reasoning. If you can write your argument into the notation form that matches one of these 8 cases, then you can simply say whether it's valid or invalid and why. So we take a look at one, we read through it, and we determine if we can draw a logical conclusion from it. So take some time to read over these and think about those using that chart. It may be helpful for you to print that slide or to print that page from the ebook and keep it next to you as you work on those assignments on your homework. Good luck.